Welcome to Study Loop.
Hey everyone, thanks for joining us today. What we're going to be looking at again is the concept of work and kinetic energy. And what we have is we have two fenders with their loading curves shown here in the graph in A and B. So A is linear, B is some sort of exponential. We're given the mass of a ship that is 90 tons and it is moving at a velocity of 1 mile an hour. And what we're asked to solve for is what is the deflection of these bumpers when that ship is brought to rest. So first thing we're going to do is we're going to figure out the slopes of the linear bumper, and what we find is that the slope of the linear bumper is going to be 60,000, round that off, 60,000 pound per feet times x, which is going to be the expression that we use to describe the force with respect to the distance. And then what we're going to do is we're going to convert the mass of the ship into pounds. So we know that the mass of the ship is 90 tons. That's the weight of the ship actually, and that we're going to convert that to 18,000 pounds. We know the velocity of the ship is 1 mile an hour, and we're going to convert that to feet per second, and that is 1.47 feet per second. Now we know that the relationship between work and kinetic energy is as follows. We know that the initial kinetic energy plus the work that's done is equal to the final kinetic energy. So we know that the initial kinetic energy is simply 1/2 mv squared, and that the boat is brought to rest, so the final kinetic energy is 0. Now we know that U12 is simply the integral of force acting up over a distance. We know the expression for force is 60,000x, so we know that U12 is simply the integral of 0 to x of 60,000 x dx. We can set this equal to T1, which is equal to 1/2 mv squared. So carrying out this integral gives us that 1/2 mv squared is equal to 60,000 x squared over 2. And solving for x, because we know the mass, we know the velocity, gives us 0.44 feet, which is also equivalent to 5.37 inches. So that is our stopping distance for fender A. Now fender B is a little more tricky because it's an exponential, some sort of exponential relationship between the force and the displacement distance. So what we have to assume is we're going to assume that the loading curve for B with respect to x is some sort of basic quadratic function. Now with simple linear curve fitting tools, you can actually plot these points and it'll spit out a rough approximation for this k value. And what I went and did was I plugged in the points 0, 0, 0.5. Remember, all these are in terms of feet, so 6 inches, 20,000 pounds. And then as well as the point 10 over 12, which was approximately 60,000. Feet or pounds. And what this gave was a k equal to 90,090. And obviously this is approximate, so the force is equal to 90,000 times x squared, and this is for B. So the approach that we use to solve for B velocities are going to be similar. So we know that the initial kinetic energy is 1/2 mv squared. Final kinetic energy is equal to 0 because the ship is brought to rest. And the work done by the bumper is simply going to be, again, f dx. We know the expression for F, which we just solved for. That's going to be from 0 to x of 90,000, 90 x squared dx. And this will be equal to 1/2 mv squared. Now, we're going to carry out this integral, and that's going to give us 90,000, 90 x cubed over 3 is equal to 1/2 mv squared. Now remember that we know, again, the value for mass and velocity because those are given to us, so we have everything we need to solve for x. And carrying out this computation gives us an x stopping distance for fender B of 7.2564 inches. And that is our stopping distance for B.